So with that, a warm good evening to all of you who are online, who are listening, and thank you, US headquarters, for giving me this opportunity to be talking to all of you. It's always a pleasure to be talking about mission operations, and like Pavitra said, I'm Deputy Director of the Spacecraft Operations area, and my team here looks after and tracks and controls all of ISRO's lower satellites as well as interplanetary missions. So today, before I actually talk to you about mission operations for solar system explorations, let me just tell you about a little bit about mission operations. So before we actually go into mission operations, let me tell you a little bit about mission planning. So all of us use the word mission and satellite very interchangeably. So what exactly is the difference between a mission and a satellite? That's very simple. The minute you associate an objective or a requirement which the satellite has to meet, or you set a goal for the satellite, then you call it as a mission. So a mission has a perfect objective, and it is designed and built to meet that objective. Now, coming to mission planning, what we do is we basically translate the entire spacecraft design into operations. So that translation is called as mission planning. But however, it's not as simple as it sounds, because it requires enormous knowledge of all the subsystems that comprise of in a satellite. And we need to know all the interfaces between the subsystems, the telemetry, the commands, and how each of the subsystem works, and the constraints with which the subsystem is operated. So this entire knowledge is transformed into the mission planning. And then it actually comes about as a person who has a multidisciplinary knowledge. He should know the perfect information and knowledge about everything that is happening on the satellite, which is obviously a very complex thing. And right from the design of the satellite to the realization of the satellite and the launch and making the satellite operation, we need to plan this entire activity, and that is called as mission planning. And of late, we also know we're just not worried about keeping the satellite in orbit. It's also equally important for us to plan the decommissioning of the satellite. So because ISRO believes, as you heard in the recent newspapers, that we believe in zero debris missions. So in order to have a successful space program which meets all the requirements of the satellite, we also have to ensure at the end of the mission life, the satellite also deorbits and re-enters the Earth's atmosphere. So now, taking on mission planning further leads to mission operations, which is our today's topic. So mission operations, if I have to just sum it up, it's nothing but an intense teamwork. And we all know that teamwork makes dreams work. And that is how we've been able to successfully accomplish missions to various planets in the solar system. Now, to quickly put the entire mission operations life cycle in a nutshell, the mission begins its job right from the time the project is conceived. The mission, what orbit the satellite has to go to, what should be the way it should be operated. The entire thing is defined in the mission design. Now, as the spacecraft is built by the spacecraft engineers, the people who also work for the ground segment also start working right at the time of the conception of the mission itself. So all the interfaces on the ground, who has to receive the telemetry, what should be the overall architecture of the ground segment, where does the data has to go from after it is being received at the control center, who are the users, how is the data disseminated. All this is a part of mission operations and the important ground segment activity that we're going about today. And these interfaces are defined and they are started built right from the time the mission is conceived. Now, as the satellite is being built in the checkout, the various subsystems are coming into the checkout and the assembly phase. We have the disassembled testing, and then we have the assembled mode of spacecraft. And this entire spacecraft is tested more, the way it is flown in orbit. We follow a philosophy called test as you fly and fly as you test. So the entire spacecraft is tested end to end. And we also test a ground segment. So that is done in the pre-launch simulation, wherein the entire ground segment for the satellite is simulated and the entire scenario is simulated as if it is a launch and as if the satellite is launched along with the satellite. So this whole phase is called as a pre-launch simulation phase. And then of course we have the launch. The launch takes place. Most of you would have seen the launch taking place on the TV. Most of the launches are telecast live. And from then on, the minute the satellite is injected into space, our tracking control center, where our team works, that is the picture in the middle, where you see people sitting, takes over the satellite and they start to track and control the satellite. So there is a phase called launch and early phase of the satellite, wherein the satellite is stabilized, the orbit is acquired, the attitude of the satellite is acquired, in the direction it looks at is defined, and all the subsystems in the satellites are switched on and commissioned and tested for the on-orbit performance. And then we get into a phase called the commissioning phase, wherein the satellite performs its objective, mission objective. So after all the payloads, if it's a solar exploration mission, so obviously, I'll be talking about the Mars orbit mission, wherein all the objectives of the mission, like switching the payloads that are there, the instruments, and the data that is collected from the instruments will be brought back to the control center and will be analyzed. So, after the initial calibration, we call as the normal phase of the mission. Right now, to give you an example, the Aditya has entered the normal phase, wherein most of the initial activities on the payloads of Aditya is over, and the data is being analyzed by the respective PAs. So very soon it will get into the normal phase of operation. And finally, we have this decommissioning phase. This is more relevant, I must say, to the low Earth orbit missions, wherein the satellite is in an orbit very close to the Earth and it can come back to the Earth. Not so much so applicable for the solar exploration missions that we're going to talk about today. So, just to summarize again, the key components that we have in the mission operations are the tracking. Obviously, if the satellite is around any planet or going towards the planet, it needs to be tracked. And we need to have a monitoring and control center, the place where we are in right now, where the data is received from the satellite and analyzed. Flight dynamics, Pavitra is from flight dynamics, their main objective is to basically assess which orbit or where the satellite is in, where the current position is, and what should be the reference orbit for that particular satellite. So they continuously assess the orbit of the satellite, and they also provide a lot of information to the ground stations and help us to track the satellite. And then the most important of all, the very reason the satellite is going to a particular planet is to perform science. So the payloads or the instruments that carry out the science are called the payloads. So the design of the payload operations and the very manifesting the payload in the way it is supposed to be, that is done again through a lot of planning and done on a daily basis. Now, scheduling is also a very important component in this entire thing, wherein there are so many satellites, especially when we talk of the solar system, and wherein you have and you also have a lot of ground station antennas, and we need to see that our resources are shared very well amongst our ground station antennas. So this part is done by the scheduling, wherein you say, if you have a deep space antenna, and if you have two satellites, one is going towards the moon and one is going towards the Mars, allocating, the schedule for each of the satellites is done by the scheduling. And this entire job on the ground segment pretty much is automated. Otherwise, it becomes very difficult to micromanage each of these components. So all of this, what I talked about, works on a day-to-day basis in an automated fashion with minimal human intervention. And all said and done, all this also requires a lot of analysis. So there are, analysis of spacecraft data, analysis of the orbit, analysis of each and every component also is a regular job of when we are carrying out operations. And finally, the product that comes, or the science data that comes from the satellite, that has to be managed. So data product management, dissemination to the users is done again by our center, wherein users of all these science missions come and have free access to this data. So let me quickly move on to, give you a rough idea of how the ground stations are placed all over the globe. The reason why we need to have ground stations all over the globe is you need to have coverage from all through the day, isn't it? So while because of the rotation of the Earth, you may not be having access to the satellite all the time. So if you have a ground station in a different location or a different latitude, longitude of the Earth, there are chances that it will see the satellite much longer after the visibility or access to your station has passed. So that is why it is important to have a network of stations so that you have a continuous access to the satellite most of the time. So we also have, transportable terminals. It's not always possible to have a ground station wherever you have a landmass. So, many times you would need to have a ground station, let's say in the middle of nowhere, middle of the sea. And then you have a requirement. You can even place these huge antennas on ships so that they can sail to a point in the ocean from where they can track your satellites. So you can see here when we did the Mars orbiter mission, the way that the trajectory that the launch vehicle took, that is on the left side corner, you see that the trajectory was going deep into the Pacific, and then you see finally there was there is no land available at the point of injection from where we could have monitored the separation of the satellite from the launch vehicle. So we set out these two antennas on the ships to sail to the middle of the ocean to track the launch vehicle. So these are some of the very important challenges that we face in our mission operations. Now coming back to our own deep space antenna, you need huge antennas which are able to track the satellites from very far off distances. So we have one such special antenna which is our own deep space network antenna, which is in Bailanu near Mysore Road in Bangalore. From where we have tracked the Mars orbital missions, we have tracked both Aditya and all the three Chandrayaan missions. So this is a bird's eye view of how this campus looks like. So now coming back to ISRO's venture into the solar system. So having told you a little bit of the various components of mission operations, we've done three Chandrayaan missions. Chandrayaan 1 was the first mission of its kind, wherein ISRO demonstrated the capability to reach the moon. So we were able to design a trajectory and actually go to a moon's orbit. And the finding of water on the moon surface, which was kind of a very inspiring story that led ISRO and many scientists to think about the consecutive follow-on mission called Chandrayaan 2. So ISRO said, let us do something more in Chandrayaan 2. So apart from reaching the moon's orbit and then operating all its payloads, let's also see if we can do a landing. And from there on came Chandrayaan 3, wherein all of you, I'm sure, have seen the recent the moon landing that happened. I'll be talking a little bit about it, and then we of course did the Mangalyaan way back in 2013 was the launch, and 2014 was the getting into the moon's orbit, the Mars orbit insertion as we call it. And more recently we've also done the Aditya L1. Let's see if I have time to speak about L1, Aditya L1. This is a that is called mission to the sun, but goes to 1% of the distance to the sun. It goes to a point called a Lagrangian point, wherein the forces between the Earth and the sun kind of neutralize, and it is a stable point. From there, you have a continuous access to see the sun, so that you can collect data all the time once we are in the L1 point. So let's move on. Let me start. I'll try to cover as much ground as possible to tell you about the solar system exploration missions that we've done and what were the operational challenges in these missions. Now, first to talk about the Mars orbiter mission. Even all of you know that we had just 18 months by the time the project got approved by the government and the launch. This was basically constrained by the launch window constraint. So when I say a launch window constraint, so mission to distant planets are restricted to short windows, wherein if you miss the window, it would not be an optimal trajectory in terms of time and fuel. So this was one such constraint that we had to work on, and it was the first time ISRO was doing an interplanetary mission. We had done mission to the moon, but to go to another planet, this was the first time we had done it. And there were plenty of challenges, to even design a hardware to survive in a Martian environment, which is very different from the environment that we have on the Earth, and to navigate and to reach a distance of almost 400 million kilometers, the farthest distance, and to talk to the satellite, in that distance, to communicate, to command the satellite, and then receive the telemetry. It required an enormous amount of mission planning and mission management. Of course, there are many other designs with respect to the hardware, in terms of the propulsion system, which had engines, had to fire after a long time, after 9 months of use to get into the Martian orbit. There were many, many more challenges in terms of the hardware. And the most important thing in terms of NSA mission operations was the autonomy that we had built on the Mars orbit mission. And why I'm mentioning this is a very critical part of mission operations for any mission into the solar system, because we talk of huge distances wherein you cannot really micromanage the satellite from the ground. So you need a lot of autonomy in order for the satellite to look after itself, at least to a great extent, till the time someone from the ground station or someone from the control center recognizes that there is a problem and can attend to it. So I'll just tell you briefly some of the challenges that we had. This is something that can happen to any mission around when you go to an outer planet, especially the sun can come in between the Earth and the planet. So if you have sent a planet or a satellite to the Mars, let's say, and the sun comes in between the Mars and the Earth, all the three bodies are aligned. There is a chance that you do not get the signal from the satellite for something like 15 days. And this can happen for longer periods when you go to a outermost planets, when you go farther and farther. So this we call as a black hole geometry. So missions to the solar system have to have a means to cope with this black hole geometry. We also have something called a whiteout geometry, whereas the sun goes behind, and then behind the ground or behind the Earth, and the sun's energy is so powerful that the data we receive from the satellite is kind of garbled because of the enormous amount of energy from the sun. So this we call as whiteout geometry. So these also can be extremely critical, and it can lead to phases wherein you do not get information or data from the satellite for long periods. So these are some type of challenges when we talk about missions to the solar system. Now, this is one of my favorite slides, wherein we had an encounter with a comet just as the satellite had reached the Martian orbit. It was called Comet Siding Springs, a comet which came from the Oort cloud, something beyond the solar system unexpectedly, and it reached Mars just at the time when our satellite had reached Mars. So when I say especially the mission planners are experts in coming out with solutions on the fly. So this was one such situation wherein we had to come up with a solution, not just to protect the satellite from the comet, the dust, but to also we got an opportunity to image the comet. And this is some of the images that we got. And we had to do some special maneuvers to duck behind Mars as the comet passed. So these are some of the challenges that you can get when you are having missions, when the satellites are going beyond the Earth. So now coming to the one of the key concepts of mission to the solar system is the trajectory design. So how do you do the trajectory design? If you have a rocket which is powerful enough to set the satellite on a path which is directly to, takes you out of the sphere of influence of the Earth. When I say sphere of influence, that is as long as the satellite is within the sphere of influence of the Earth, it tends to keep going around the Earth. But if it needs to go towards any other planet, if this rocket is powerful enough to set you on that direct trajectory, then we have no issues at all. But here we were talking about a rocket using our own PSLV, and we had to do many orbits around the Earth in order to gain energy to go out of the sphere of influence of the Earth and go into a heliocentric phase, what we call, towards the, in this case, a diagram which could be the Mars. So you get into a heliocentric phase, and finally there is a time, it's more like a rendezvous problem. While the satellite approaches very close to the planet, it needs to get captured into the sphere of influence of that particular planet. Otherwise, it would become just a flyby and brush past the planet. So these are some of the things that we need to take care very well while we design our trajectory. Now, when we're talking about MOM, so we did this kind of a trajectory planning, and we were trying to aim at Mars, which was almost 650 million kilometers away when we actually the satellite left the Earth. And it's not just about planning the trajectory, it's also about knowing if you're on the right path on the trajectory. So that is done by various complicated methods, which we call as the orbit determination. To know exactly where you are on the trajectory to the planet is also an extremely critical activity. So apart from that, what are the other challenges that we face when we are going towards a distant planet? Like for example, in Mars, in the case of Mars mission, the distance that at the speed of light taken from Earth to Mars was a maximum of 20 minutes. So if you had sent a command, we could easily have a cup of tea and come back before we actually knew the command had reached the satellite. So we are dealing with this kinds of huge delays, even traveling at the speed of light. It could probably take hours when we are looking at talking to a satellite which is going to a distant planet. So we need to have a lot of features available in the satellite to take care of this kind of a delay. And beyond that, when you are receiving the data from such a big distance, the signals have to pass through a gamut of radiation, space radiation that degrades the clarity. It is like, picking up a small whisper if you're sitting in a cricket stadium amongst that big noise. So the receivers here have to have this extreme sensitivity to pick up this kind of a signal. And to make it harder, all the planets, the satellites, everything is constantly in motion, including the Earth. So the geometry of these also makes it sometimes extremely hard. And like I mentioned, the blackout and whiteout is one such scenario wherein the dynamics of all the planets also can create a problem when it comes to mission operations. Now, these were some of the challenges. So all of you know, I'm not going to be talking in detail about what happened in the Mars mission, but being the first country, to reach Mars successfully in the first attempt. It was appreciated a lot, and there have been a lot of accomplishments that this mission had. It lived for more than 8 years, much beyond the mission life of 6 months that we had anticipated. One of the biggest, I think, the most image that was appreciated most was this image, wherein we got the full disk image of mom in just one frame of the camera. And these are, we could take a picture of the Mars within 40 minutes of getting inserted into the Martian orbit. And that is why this image is extremely special. So we are also looking at, Mars orbit mission could look at various volcanoes in the Martian surface. Olympus Mars is the highest volcano in fact the entire solar system. So these are some of the images. Let me just quickly brush past through this images that we have taken. Now let us come to our lunar missions. We know that number of countries try to go to the moon, and we've had many successful attempts on moon landing, but of late we also had many unsuccessful attempts by other countries too. But lunar landing is an extremely complex activity. Why? Because unlike what happens on the Earth, here none of us go out of the home without our phone, more to use it for the GPS and navigation rather than the phone itself. So obviously you don't get GPS signals there, and what makes it very challenging to do a moon landing is there is absolutely no atmosphere. So all the reduction in the energy while the landing is to be done by the engines themselves. In Mars landing, because it has this atmosphere, you can use parachutes and deceleration systems to do the landing. Whereas even when you have a crew written on the Earth, you can have an option to land on the sea, wherein you can, apart from the parachutes, you can have a flotation system to recover the module. But moon landing is extremely hard because of these conditions. So now, what exactly happened in Chandrayaan 2, but I'm not going to be dwelling a lot in Chandrayaan 2 because we hardly have, you all seen this many times on TV and more recently. So we had various components. We had a very good launch vehicle which took us to an elliptical orbit. We did a series of earth burns like we did in the Mars orbit mission to gain that extra energy to go towards the moon surface or the moon itself. And once we were captured by the moon, we did a series of burns to get into the closer and closer in the moon's orbit. And then, of course, all of you have seen the moon landing more recently. And the most challenging and exciting part of the mission was the movement of the rover. Let me just show you let me just skip this slide. This is what I was explaining. Let me just show you a small animation of what happened during the mission. This is just for some of these very nice pictures on how the Chandrayaan 3 was built, and this is how the landing took place. And when I just explained that how complex it is like the module had something like 1.68 kilometers per second velocity, more than in terms of what you actually measure on our roads. More than 6,000 kilometers per hour velocity or speed that we have. That had to be reduced to almost zero to do the landing. Apart from that, there were many, many challenges which probably I can explain some other time. So this is how, you can see that the landing was taking place. These are pictures taken by the onboard camera. And yeah, and I don't know if we can see this. Yeah, let's just go further. And should I show this? Yeah, maybe I can show this animation of what exactly happened. There you can see that the lantern has landed, and then you can see that the ramp is getting deployed. This is basically a ramp for the rover to come down, and there you see the ramp coming slowly down, and you can actually see the rover moving down. Let me just accelerate a little bit, And yeah, the rover comes down. Yeah, these are very exciting pictures. That these are actual pictures taken from a camera which was sitting on the Chandrayaan-3, and it actually saw the rover coming down. And all of you please recognize the Indian flag and the Ashoka symbol there. And then the rover has moved ahead, and you can see the tracks of the rover there. And then you will see this rover doing a small swirl at the end. Yeah, there it is. The rover is doing as well. So that's it. So yeah, so let me move on. So the rover actually moved on the moon surface. The rover was communicating to the lander, and the lander was communicating to the Earth station here. The IDSN picture, the Indian Deep Space Network picture that I showed you earlier on. And these are some more very nice pictures from the Chandrayaan itself. You can see, when once the rover was moving, we had reached a point there wherein we saw craters all around, and we really could not move ahead because three directions we had turned, and all the three directions we had found craters, and so then it was decided the rover should do a backtrack. And you can see the places that the bottom picture here. You can see the rover moving backwards, and you can see two tracks there. That was the rover coming back in the reverse gear. So this is some of the fun features that we had. And this is how the Chandrayaan-3 rover moved the days that nearly moved 102 kilometers. So now, why is it important? Now let us move on from ISRO's missions to what we can do further in the solar system. So one thing that I think all space organizations today are thinking about is to have the moon as a base. What do you mean by saying moon as a base? So moon should be a place wherein any future missions to any other planet, we could use moon as a hub. Moon as a hub for landing and then further going to different planets. Moon as a hub for communication. Moon as a hub to also declare us or becoming a type 2 civilization on the Kardashev scale. So, it's also important for us to think beyond Mars and Moon today. So we should know and we should be working on how to build and operate an extraterrestrial base. And we also understand the impacts of living in space. The effect of all this radiation, space radiation on the human body and on the various instruments. So all this is something that we will learn if we have a base on the moon. And once the hub is fully operational, you can have many things. You can even exploit the moon moon surface for various minerals and energy. So this is one of the aspects to have moon as a gateway. Further beyond, what next? So we have many other, our immediate neighbors, the Venus and Mercury. Venus is, let's say, almost you can say it's as big as the Earth. But there are a lot of similarities, but it's also extremely different. It's extremely hot. So one rotation day and one revolution day is almost same on the Venus. It's almost equal to 243 Earth days. And of course, it's the closer planet, but it is hotter than Mercury. So that is why missions to Venus are extremely challenging. Apart from the Venus's atmosphere itself, the thick sulfuric acid clouds that surrounds the Venus. So these are some of the prospective missions that we can possibly have. We can have. So, but going planning for the to reach different planets is not an easy job. Since this topic today is on mission operations, the most challenging aspect is to find the best trajectory or the most optimal trajectory to reach these planets with spending minimum amount of fuel. Now there is various methods to do it. Now let us see one of those methods which most organizations employ is the gravity assist. wherein you can increase or decrease the energy of your satellite just by going close to the planet in a particular direction. So you can actually use the gravity assist of Jupiter to go to Saturn. You can actually use the gravity assist of Earth to go to Jupiter. So a lot of these things are being used, techniques are being used today so that we do not spend so much fuel to reach these farther planets. Because if the entire energy to reach to the planet has to come by either the chemical energy or the whatever, even the RTGs, it is not really feasible to carry so much fuel, and because it becomes extremely expensive. So this is one of the very good techniques to go into the farther into the solar system. Now, having reached the solar system, you still having reached a planet in a solar system, you still need to go closer into the orbit. Let's say you're going to the Venus. So having reached Venus is one part, but getting closer to Venus to operate the payloads is another part. Again, do we need to spend fuel to get into an orbit closer to the Venus in order to do any meaningful science? So here, again, there are many new techniques. One of the techniques is aerobraking. So wherein we use the the drag that is there in the atmosphere to reduce the orbit. So what is done, if I have to explain it very simply, the concept of aerobraking, what is done is the satellite is maneuvered close to the surface, or we call the periapsis, in order to experience the maximum drag. So once the satellite experiences the drag, automatically there will be a reduction in the energy and the apoapsis will reduce. So this is a constant, every time we pass through the periapsis, there can be a reduction in the apoapsis naturally coming out of the drag. So this is one concept that people use called aerobraking. So let us go further. Now we have our sister worlds. I already explained to you that Venus mission to Venus could be extremely challenging, whereas we on Earth experience temperature something like minus 88 to 58. Now the deep down in Antarctic somewhere could be minus 88, but when you look at the temperatures of Venus, the surface temperatures are something like 462 degrees centigrade. If you have to go or design a satellite to Venus, we need to take care of this aspect also, which is extremely hot. And apart from that, there are many, many more challenges. The sulfuric acid clouds around Venus makes almost extremely difficult for any payload to be operated. Like an optical camera would just not work. So mainly we would look at something like a radar or payloads operating in a microwave region in order to get information on the surface of the Venus. So these are some of the extremely big challenges that we are going to face when we are going to go to this planet. Now, many people have already, many organizations have tried to do missions to the Venus, and this mission to Venus is also one of these things probably ISRO will look for in the future. Now, coming to the end, I just want to tell that the first man-made satellite to go beyond the solar system is Voyager 1. Today, Voyager 1 has reached the heliopause. It is a marvel, I should say, and for most of us doing mission operations, it is something that we all can dream about, to send a satellite that far to go beyond the solar system and still continue to receive data and information. So with that, I end my presentation today. Thank you so much for your patience and for listening. Thank you so much.